problem tells a story about an airplane pilot that fell out of his plane. And part A has to do with the second part of what happened. And so first he fell out of the plane, he fell through the air, and then he landed in the snow. And so part A starts with the idea that he lands on the snow, and at this point he's going at terminal velocity. And so you ask yourself, what kinds of energy does he have? And so you think, well, he has kinetic energy, obviously, 1/2 mass times the terminal velocity squared. And if we want to say that the zero of height is here, that means he doesn't have any gravitational potential energy and he doesn't have any elastic potential energy, so his total amount of energy is this. Then they tell you that he gets buried in the snow. So there's our zero level where the top of the snow is, and now the pilot is down here some distance, which I'll call D, that he's been buried in the snow. And at this point, he has no kinetic energy anymore because he's stopped. And we're going to say he doesn't have any potential energy either because we're allowed to neglect that. So his potential energy is also zero, which means his total energy is zero. Well, what happened to it? In between this picture and that picture, work was done. So work is always equal to FD cosine theta. And in this case, we're going to call F the force from the snow. D is this D right here. And cosine theta is -1 because the force is up, the displacement is down, so they're opposite each other. That means that the cosine is -1. So my work then is minus FD. And if I put this all together into an equation, I see that 1/2 mv squared minus FD has to be equal to the ending thing, which is 0. So that tells us that this equals that, and from that we can calculate, well, we can actually calculate both things. Part A asks us to calculate the work, which is equal to the FD, which is equal to 1/2 mv sub t squared. And this is probably the easiest way to calculate that work. In part B, they want you to find the force. So now that we've calculated the work from part A, we're going to make that just equal to FD. We know the distance, so we can calculate the force. Then there's part C. And in part C, now they're talking about the beginning of the story, where in the first picture, the guy has just started to fall and he has no parachute. So way up here, he has a potential energy equal to mgh, and he has no kinetic energy yet because he hasn't started to fall, but he will very soon. There's no elastic potential energy, there's no spinning energy, that's all that's going on. And then later in the story, he's fallen down to the snow, right? So that's like this picture. So he's fallen to here, where his potential energy is now 0, and his kinetic energy is equal to 1/2 mv sub t squared. But in between these two events, work took place. What happened was the air resistance slowed him down to terminal velocity, taking some of the energy away. So in here, we're going to have negative work being done by air resistance. And I can make this into an equation. I can say that mgh minus the work done by air resistance has to be equal to the total energy over here, which is 1/2 mv sub t squared. And all they ask you for is this work. So all you have to do is plug in the numbers which you know from before, and plug in those numbers, and you can